It is my privilege to be the chair of this section, the plenary invited speakers. My name is Esmond Ng from Lawrence Berkeley Lab. The first plenary invited speaker this morning is Dr. Haohuan from Tsinghua University in Beijing, China. Dr. Fu received his PhD in computing from Imperial College London. He probably doesn't need any long introductions because as he's probably quite well known in the SC community. Last year he was a member of the team that won the Golden Bell Prize in SC17. In addition to being a faculty member at Tsinghua University, Dr. Fu is affiliated with the Key Lab for Earth Systems Modeling, and he's also the Deputy Director of the National Supercomputing Center in Wuxi, which is where the #1 machine is located at the moment. So Dr. Fu will talk to us about the decision process in designing the Haohuan supercomputers and the use of the machine in solving science problems. So please join me in welcoming Dr. Fu.
Okay, good morning, everyone. Thanks for the introduction from Esmond. It's actually my great honor to be here and to share with you some of our recent experience, say in the last 2 years, on using this machine with over 10 million cores. So as Esmond introduced, I will talk a little bit about how we actually make our design decisions about the processor, the system, and also how we actually scale the applications to the 10 million cores of the system. Okay, so since it's the first time that I have the opportunity to talk to you about this system, I'd like to take some time to actually acknowledge the great efforts that these organizations have done to make it possible to have this machine and also to have application software on this machine. So our major sponsors, the Ministry of Science and Technology in China, Jiangsu Province and City of Wuxi, they are actually providing the 1.8 billion Chinese yuan budget to build this amazing machine. And also I'd like to mention that City of Wuxi is so kind that actually also support the electricity cost, which as you can imagine is a big part of the operation cost. Now, they did threaten us, right? They're going to cut the budget gradually, year by year. But I guess there's also a good motivation for us to convert some of the science into service and trying to become self-sustainable as a center. And the winner, as you may already know the name quite a few times, the National Research Center for Parallel Computer Engineering and Technology. So this is an organization with thousands of experts and engineers that works on the design of both hardware, software, and the integration technologies. So as I will talk later, they really have done a great job to put together a very good machine. And now you see all these logos. These are actually our, I should say small, but growing ecosystem of developers that actually write software on this supercomputer. As you can imagine, for a system like Sunway Haohuan, with such a high performance and good efficiency, is taking a hardware architecture that is completely different from the previous one. So as a result, we don't have any software that we can grab and run. So we have to spend a lot of efforts to actually put applications onto this new supercomputer. So without them, I don't think we could be able to make so many exciting application results in the last 2 years. So also to introduce to you this machine, okay, that's my time for free Chinese lessons. If you see the name, okay, so in English and also in Chinese, so this first word Sunway actually corresponds to the two Chinese characters, which literally means God's power. So you can see the NRCPC, the organization, is really ambitious about making really good supercomputers. Now for the exact name for this supercomputer, Taihu Light. So these two characters, actually, in Chinese, in Asian Chinese, it means huge lake. Okay, so it's actually the name of a very big lake in the eastern part of China, very close to Shanghai. If we zoom in, you can see the lake and all the cities around it. So we are located in the city of Wuxi. And I guess just from the map, you can see that this is probably one of the most developed regions in China. And all these cities, so we also have a ranking of top 100 cities, depending on their GDP. So a lot of the cities, Shanghai, Suzhou, Wuxi, and a bunch of others, they are actually among the top 100 cities in China. This is actually very important. Remember, we have to be self-sustainable. So the economic strength in this area is actually going to be important for us to support the machine and also for us to bring benefits to the industry around this area. Okay, so now let's come to the technical part. So in the first half, I'd like to talk about the machine, about how we actually design the processors and how we integrate them into a unified system. So a little bit about the history. So as I mentioned, Sunway is actually the name of the family of supercomputers. So the first Sunway machine, Sunway 1, was built in the year of 1998 using commercial processors. And it was installed in the weather forecasting service. And it had the very great honor to provide weather forecasting service for the Great Parade on the Tiananmen Square next year for the 50-year birthday for the People's Republic of China. Now, Sunway Blue Light is our first system using our own processors, a 16-core processor providing a peak performance of 1 petaflops. And so right after that system is finished, around the year of 2012, 2013, NRCPC starts the project to build the next generation. And they are pretty ambitious. As you can see from the target, they want a system providing a peak performance about 100 petaflops. So that's 100 times faster than this generation. And also it has to be a homemade CPU. So actually the first question is to design a competitive processor that can actually support this kind of supercomputers. So around that time, 2012 or 2013, a lot of the leadership supercomputers are already taking many core architectures. As you can see here, we have K20 for the Titan, and we have the Night Corner for the Tianhe 2. And their peak performance is somewhere around 1 teraflops, with a power efficiency around 2, from 3 to roughly 5 or 6 gigaflops per watt. So our CPU design goal was set to be 3 teraflops per chip. Okay, that's just 2 or 3 times faster than the existing many cores, but from the previous generation is a jump of 21 times. And also the power efficiency, we wanted to be 10 gigaflops per watt for this processor. Again, 5 times jump from the previous generation. So apparently this is not an easy design task. When you come to the design of processor, it's always an optimization problem with a fixed constraint, because you only have this large area of chip that you can use. So you have to decide which part you put your resource to. So in our case, our strategy is very aggressive towards the computing power. And we are adopting very simple cores. Our strategy, as I put here, simple for more. So we put simple cores, and we put a lot of them, and we put wide vector units to further push forward this computing throughput that we can get. And because we are putting all this resource to the computing part, for the memory hierarchy, we have to give up something. So we don't have L1 cache for the computing, for most of the computing cores in this chip. Instead, we provide a scratchpad buffer, which, as you can imagine, could be good or bad, because now you have to really deal with the memories by yourself. And also to further increase the data sharing among these different cores inside this processor, we add some special architectures to support inter-core communication and also synchronization of these different cores. Now, for the general architecture, we actually take a similar approach as the previous generation. So inside the CPU, we have 4 core groups. Okay, so I think it's a divide and conquer strategy for this one. So here you can see the actual architecture of this processor. We have 4 core groups. So each of them comes with one, what we call MPE, a management core, which is more similar to the traditional CPU cores. So it can do all the different kinds of tasks: compute, management, communication, all the things. Now the main computing power actually comes from the 64 CPU cores, the computing cores. So they are organized as an 8x8 mesh. And as you can see from these figures, the memory hierarchy, as I mentioned, is different. Instead of L1 cache, we have a 64 kilobytes of fast buffer for each of these CPU cores. And also, we have added these communication rows and columns, so you can exchange data among these cores very efficiently at the level of registers. So, as you can see here, it's really a very different architecture from the previous generation and also from other architectures that you have on the market. And with this architecture, this processor provides actually 3.06 teraflops per chip. And for each of the nodes, we just have one of them. And then we have 32 gigabytes of memory. The memory bandwidth is not very high. It's 136 gigabytes per second. It's DDR3 memory. And as I mentioned, it's divided into 4 core groups. OK, so that's about the processor. Then with the processor, how do we actually integrate them into a supercomputer? So we have this, what we call a 5-level integration hierarchy. So on this very small board, we actually have 2 of the computing nodes. And then we put 4 of these kind of small boards into a large, what we call a sandwich board. So we actually have 2 of them on the top and 2 of them at the bottom. And the cooling liquid is going through in the middle to take away the heat from the processors. And then we have 32 of these things to form what we call a supernode. So in this supernode, we have 256 processors. And we have a customized network board sitting behind to achieve a fully connected interconnection between all these 256 processors. And then we have 4 of them to actually form a cabinet, and 40 of them to form this supercomputer with a peak performance of over 125 petaflops and over 10 million cores. So if you can look above, our machine looks like this, what we call a 0-1-0 architecture. The 2 zeros are the computing parts, and this 1 in the middle is the network system. And as you can see from the bottom, that's how we get our 10 million cores in the system. So here is just a very simple comparison between our system and some other supercomputers. As you can see, the advantages and also constraints of this system is very clear. We have a great advantage over other systems on the computing power, on the impact performance. But in terms of memory, we are just similar or even slightly less. For example, for K computer, we have 10 times more computing power, but our memory is actually slightly less. And also the bandwidth, as I mentioned, the bandwidth per node is also not very high. So as a result, you can see we are #1 in top 500 for Limpack, but for the other benchmarks for Graph and HPCG, we are not performing very well because of the constraints from memory bandwidth. But in the later slides, I will introduce how we can actually get around these memory barriers and get really good performance from the applications. Okay, so before going into the applications, I'd like to talk a little bit about the plans for the next few supercomputers from the Sunway family. So somewhere next year, we are going to have a new Sunway system, not as large as this one, probably around the size of 5 to 10 petaflops, but it will be a middle point along the journey to exascale. So it's basically a pilot system to evaluate our technology, especially for the processor. So the target is 5 to 10 teraflops per node, and we want to improve the power efficiency to 10 to 20 gigaflops per watt. So that's the middle point. And around the year 2021 or 2022, we're going to have the exascale Sunway machine with 1,000 petaflops peak performance, and the target power efficiency is 30 gigaflops per watt. Okay, so that's about the machine. Now let's take a look at the applications. Now, the main reason that the government wants to spend this much money to build a system is, of course, they want this machine actually to enable better solutions for cutting-edge science and engineering problems. But to do that, you need something to connect from the machine to your scientific or engineering problems. That's your application software. And this is probably one of the toughest challenges for us, for Sunway Taiko Light, because as I mentioned, it's a totally different hardware architecture, and we have to actually grow our own ecosystem for developing these different softwares. And there are also other challenges. I listed here 3 key questions we would like to provide some answers in this talk. So the first one is about the scale. So Taiko Light is the first system in the world with a parallel scale of over 10 million cores. So for your application, for your algorithm, how you can actually design it to scale to this level of parallelism. And also, how do you utilize this different memory hierarchy? We don't have everyone cache, and we have a relatively limited memory bandwidth and memory size. So how do you deal with that? And also, as I mentioned, the existing science code, which accumulates the science discoveries in the, probably the last few decades, how do you migrate that onto this new architecture? So, as Esmond introduced, I'm from the Department of Earth System Science. So climate modeling is one of my sort of major fields. So I'd like to first provide some answers about both the scaling and also how to migrate the software with some examples from the climate modeling field. So climate models is one of the traditional applications running on the supercomputers, and they are growing. For the first supercomputers in the world, climate models are probably also the first few applications, but at that time they only have maybe just the atmosphere model. And then they add the ocean, and then they add the sea ice, the land. And as you can see today, they're trying to add all these different things. Especially in China, we have to add the atmospheric chemistry. That is very important for dealing with the smog issues in large cities. So you have more and more science that you want to put into it, which calls for more computing power to deal with them. And you want better resolution. You want to simulate hurricanes. You want to simulate eddies. You want it to be cloud resolving, eddy resolving. You have to improve the resolution. And of course, improving the resolution by 2 times, your computing amount is probably multiplied by 8 or 16 times. So that's another increase. And the physics is also becoming more and more detailed. And if you want to actually do prediction, okay, this is an image I borrowed from a scientist, a climate scientist from a K computer. You have to actually do ensembles. You can't just run one model. You have to run different models or run the same model with different initial conditions. So in K, they actually, they run 10,000 different sample sets. So you can see, now this is not just for demonstrating the K computing power. They do it because it can actually improve the prediction accuracy for sudden rains. So you can see that's another front of demand. So with all these things combined, I borrowed this slide from NCAR. You can easily justify that. You can use, exascale or even, as shown in the video, zetascale supercomputers for this kind of problems. But then there's always the gap. Like in China, we already have very good supercomputers, over 50 petaflops, over 100 petaflops. But if you look at the climate models, most of the climate models in China, the operation models, they are only using the scale of computing resource around maybe 100 teraflops. They are pure CPU, and they only scale to a few thousand CPU cores. Now, part of the barrier is, of course, as I mentioned, there's millions of lines of lexicode, and they were not designed for this kind of scale of parallelism, and also not this kind of many-core architectures. So how do we solve that? We had two projects to solve this kind of problems. So one is to design something really scalable that can really scale to the 10 million cores, 10 million heterogeneous cores in our system. That is the first part I'd like to talk a little bit, which also provides some of our own experience about scaling to the level of 10 million cores. So before going into the algorithm, I'd like to first introduce to you the programming model on Taihu Lite. Actually, is quite similar to other heterogeneous supercomputers. Is MPI plus X. So at the top level, you still have the MPI to manage different nodes, and in our case, different core groups. So usually we assign one MPI process to one core group. Now, within each core group, we have 65 cores. And for them, we use either OpenACC or ACRED. So that's just like OpenACC or CUDA. You can decide whether you want to do it in an easier way or more difficult way, but better performance. So that's the two interfaces that we provide. So to scale is also a two-level thing. At the first level, we have to scale to up to, at the maximum level, 160,000 MPI processes. And then inside each MPI process, we can have 64 or 65 different threads. So when you design your algorithm, you have to think about it slightly different from before. You have to reserve enough parallelism for the 65 cores in each core group. Or actually, in most cases, you probably want to redesign your algorithm. You want to have this kind of what I call local parallelism, because they are going to be running in the same core group. You want to have some locality in the compute and the memory access so that you can utilize these different hardware features in our processor. Okay, so let's come to the algorithm part. So in this one, we were trying to design a solver for the atmospheric dynamics for global simulations. And what we choose is an implicit approach. So that means we have to design an implicit solver that can actually make very good utilization of all the 10 million cores in our system. So as I mentioned, we divide it into two parts. The first part is about the MPI parallelization design. So in this part, we are using a combined of domain decomposition and multigrid algorithm. Now, our multigrid is a little bit different if you compare our work. So this is actually our work that won the Golden Bear Prize last year. If you compare this work with the Golden Bear Prize winner the year before, they are also implicit solver. They are also using multigrid, but they have much deeper levels. In our case, we use a much shallow. We only have 3 different levels for the multigrid. And the reason for doing that is because we want to reserve enough parallelism for the multi-threading stage afterwards. And also for the domain decomposition, we have regular decomposition blocks. We have a uniform domain decomposition so that we can have all these small blocks that we can then plug and play with our subdomain solvers. Okay, so that's the first part of the algorithm design. And the second part, we need to figure out how we actually design a subdomain solver that can very efficiently utilize the 64 CPU cores in this architecture. So we set up a few goals. The first thing, we wanted to be a single sweep of all the data points. As I mentioned, the memory bandwidth of our system is very limited, so we just want to load them from the memory for just once. And then we want it to be synchronization free. We want the threads to compute in parallel. We don't want them to do too many synchronizations. And also, we want a very good data locality. So to achieve these three goals, what we come up is what we call a GP IRU preconditioner. So this is the first part of the solver. The other parts of the solver are actually easier to implement on this many-core architecture. So as you can see from the figure, we actually have multiple pipelines that goes on in this algorithm. So first, along the pencils, along the z-axis, we have a thread. So for each pencil, we assign a CP thread to process this pencil. And then along the plane, we actually have another pipeline. So in this stencil, it's similar to other stencils. You would have the point to access the neighbors to do its computation. So we start the thread at the corner first. And after it generates the data needed by its neighboring threads, we use the register communication feature to feed the data to the neighboring threads. And then after the neighboring threads get the data they require, they can start their computation right away without to perform a synchronization or something like that. So in this way, all these 64 CPU threads could be performing their computation quite efficiently. And combining these two, we can then have an algorithm that can actually scale to the 10 million cores of the system. So this is our strong scaling results. As you can see, for higher resolution of 2 kilometers, we actually have a pretty good number of 67% strong scaling result. For 3 kilometers is 45%. And the other curve is the results for the Golden Bear Prize the year before. They were based on a homogeneous machine, and their efficiency is somewhere around 33%. So you can see this algorithm actually achieves very good performance on our supercomputer. Now, in terms of the flops, so as you can see here, for the implicit solver we did on this supercomputer, our sustained floating point performance is roughly around 8 petaflops, which is pretty good for an implicit solver. So the other thing that we did in this work is actually at this scale, we compare an implicit approach with an explicit approach, which is also optimized on this Sunway Taikulaite supercomputer. So if you look at the flops, of course, the explicit solver is providing a floating point performance of roughly 23 petaflops, much higher than the 8 petaflops of the implicit solver. But if you actually compare the speed that you do the simulation, like how many years that you can simulate with a day, this implicit one is actually roughly 90 times faster than this explicit solver. Now this is still at the solver stage. We still need some extra work, maybe another 5 years to convert this into a practical dynamic solver. But this shows some potential of the implicit solvers in the atmospheric dynamic problem. So this is the first example I give as to how to design a really highly scalable algorithm that can make very good utilization of our system. Now, the second example I put here is about the other part, about the legacy code, how you can actually migrate the existing science code onto this machine. So actually, even before the Sunway Taikulaite supercomputer was accomplished, we started this project trying to port CESM, the Earth system model, onto this new supercomputer. which contains all these different components: atmosphere, ocean, land, sea ice. Now, the porting itself takes roughly 1 month. Now, when I say porting, I just mean we can compile this code on our supercomputer and make it run. It does not mean it's really taking advantage of all the many core architectures in this computer. So the second stage is actually about the CAM, the atmospheric part. We're trying to actually refactor and redesign this part, so really make it suitable for this many core architecture we have and to get very good performance out of it. So in this one, of course, the challenges are quite different. Right? You have this heavy legacy code, millions lines of code. And for climate model, you don't have clear hotspots. It has so many different functions that can actually consume your compute cycles. So you have to really refactor all of them, or you don't get very good performance improvements. And also this misfit, the legacy code was designed for multi-core architectures. For many core architecture, especially for our architecture, without L1 cache, with only 64 kilobytes of scratchpad memory, is actually very difficult to get good performance. Now, the biggest challenge as I see in this project is, of course, the lack of people. We don't have people that actually understands both the climate part and the many core part. So if you see this figure, we have a bunch of lovely faces, but after the 3 months initial projects, many of them have come to their supervisors saying that they want to switch to another topic, like deep learning, So this is really a challenge. If your PhD student is working on something that he has no understanding, it's of course very frustrating. So in our case, we are doing this thing as 2 parts. For the atmospheric model, we have the dynamic part, which is more regular code. We can do some manual transformation of the loops. For the physics parts, which is the most difficult part to understand, we have to rely on some tools to perform the loop transformation, to make it into the form that actually suits both our compute patterns. So remember, we need 64 threads for each core group, and also fits the 64 kilobytes of fast buffer of each of these CPU cores. So after doing this transformation of loops, after the OpenACC-based refactor, we were able to scale the CAM code to around 24,000 MPI processes. That's roughly 1.5 million cores in our system. The performance is roughly 3 simulated years per day. For a high-resolution simulation, this number is kind of acceptable. But if you compare that with the Intel platforms, it's just the performance provided by one core group is just slightly better than one Intel core. So to continue this effort, what we want is really from the 65 cores, we want some performance equivalent to at least a couple of Intel cores. So based on our OpenACC refactor code, we go even further. We do an even more aggressive redesign strategy to rewrite some of the codes into, as I mentioned, the A thread, the more low-level but much better control of the performance, so that we can have finer memory control, we can have better vectorization. And also, in the second step, we can actually also redesign a lot of the parts to take advantage of the register communications. As you see in the figure, it's an example, a very common operation that you have to add a colon of numbers. If using OpenACC, we can't really take advantage of the register communication features. So after doing all this redesign, you can see that we can now get some decent performance. So the first bar is right after we port the code. That's just using the MPE. So the performance is very poor, just equivalent to 1/3 or 1/5 of Intel core. After the refactoring, we can be somewhere close to 1 Intel core or 2 times better. But only after redesign, we can get somewhere roughly 7 Intel cores, or even in some cases 1 core group that is 65 Sunway cores can be equivalent to 43 Intel cores. So that's really the kind of performance we want to see on this supercomputer. But to achieve that, for the code that was designed for some ProOS architectures, you really want to redesign a lot of the algorithms in that. And this is actually also one of our works that has been selected as the Golden Bell finalists this year. So if you want to learn some more details, you can come to our talk later today. So the other thing is about the memory barrier, as I mentioned. We have a relatively higher memory wall than other systems. So how do we deal with that? To talk about the memory barrier, if we compare our system with Titan, node to node, so each node we have 2 times better computing performance. But if you look at the bandwidth, we are only a half of that, which means in terms of memory, we are 4 times more challenging to get some efficient design on this system. So in our case, we have 2 weapons that we can use. The first thing is to design a specific DMA scheme for your application. So you load the data into the buffer, and then you do your compute. And you want to do it in a careful way so that you can actually overlap your DMA operations with your compute operations. The second weapon, as I mentioned quite a few times, the register communication is something that you have to use to achieve very good data reuse. So an example for this one is the earthquake simulation that we have performed on this supercomputer. The main part, the seismic wave propagation part, is based on the very famous AWP ODC code. So this is a finite difference code, as you can imagine, is very memory bandwidth constrained. So first, of course, we still need to design a very good parallelism scheme to scale it to the 10 million cores. In this one, we have very good parallelism along the MPI process. So most of the design is actually about the CPEs. We have to do the blocking, and we have to use the different CPE threads to compute, again, different pencils in your 3D blocks. Now, the key problem is about the memory. How to deal with the memory problem. So as I mentioned, we have to design a specific DMA scheme. And one of the advantages of our CPU core is that we actually have 2 instruction pipes. So one for memory operations and the other one for the compute operations. So as you can see for the figure on the right, when you compute the slice of number 3, you can actually issue the other instructions to do the DMA load for the slice 6. So for each CPE, actually you can have the advantage to overlap your compute and your DMA operations. And within each core group, all these 64 threads, they also provide the very good advantage of multi-threading to hide your memory latency and to maximize your memory bandwidth throughput. And we also do array fusion. So in this problem, each grid actually has 30 to 40 variables. So 30 to 40 3D arrays that you have to deal with. So we have to actually analyze the patterns and put the arrays with the same compute and memory patterns together so that we can sort of use a larger block size and improve our memory bandwidth utilization. And also, a very good feature of our system, we can use register communication to exchange the halos, which is a very important part for the stencil operations. Now, after doing all these kinds of optimizations, as you see from the numbers, we are pretty much pushing towards the limits of the memory capabilities of the machine. Now, if we want to go further, if we want to go beyond that, what can we do? We added the on-the-fly compressions. So we store the seismic data in the compressed format in the main memory, and then from the local data buffer, we then decompress, compute, and compress back. Now, of course, this kind of compression scheme, if you want to make it to improve your processing speed, is very complicated. And we have actually made quite some optimizations to achieve that. So the results, as you can see here, without compression, our seismic propagation code can provide a performance of 15 petaflops, which is quite good, considering our limited memory bandwidth. And if we add compression, we can further improve the performance by another 24% to the stage of 19 petaflops. Okay, so that's the sort of the efficiency of utilizing this machine. So again, we will have a Golden Bear talk today about some more details. If you are interested, please come and join our talk. So one last thing I want to mention a little bit here is about, I said, where your PhD students go for deep learning. So we also have a deep learning framework on Sunway, trying to support scientists to do analytics job on this machine. So we have Sunway DNN, which is equivalent to cuDNN, and we also already have a version of Sunway Cafe. And we are working with Baidu to port the paddle framework onto our framework. So the current performance might not be that good because our processor was not designed for deep learning, and it was not designed for single precision operations. So actually, as you can see here, our single precision performance is even worse than the top of precision performance. But one processor, at least, is equivalent to 1/2 of NVIDIA K40. And we are already starting large-scale training with Sunway Cafe on our supercomputer. If you have been to Mr. Yu Yang's talk, yesterday was the day before yesterday, following a similar approach, we can support a 32K batch size, and using roughly 1,000 nodes, we can finish the ImageNet training in roughly 2 hours. But that's because there are some parts of the code that are still not optimized for this architecture. With further optimization, I think we can improve that to roughly 1 hour. So again, some more acknowledgments, especially for the 2 Golden Bear works this year. The CAM work, we received a lot of support from our friends in NCAR, and the earthquake simulation work. Special thanks to Dr. Yifeng Cui. He actually initialized a lot of the collaborations between our center and SCAC. Okay, with that, I should end my talk. Thank you.
Thank you. We have time for maybe a couple of questions. If you have a question, please come up to the mic. They are in the middle of the aisle. So let me ask you a question then. I don't know if there's an answer to it. Do you have any estimate from the time you decide to port a code to the new machine, or maybe redesign the code or refactor a code, roughly how much time it takes in order to get to the best performance?
Well, I guess that's quite different. As in these 2 examples for the seismic code, which apparently has a very clear hotspot, I think it's just 2 months or 3 months time. But for a very complex scientific code like CAM, we are already doing it for like 2 years, and we are still continuing our efforts on that. So,
okay.
Yeah.
Thank you. I think we have a question on mic number 1.
Okay, and I have one question about the manual transformations you used. Do you expect every application to use the same process?
No, we don't. Actually, we don't want that, actually. So for the engineers in our center, I think they're already tired of doing one application after one application. And I think till this stage, we already accumulate quite some experience about both this architecture and also these different scientific kernels. So from this year, we're already starting developing some tools, trying to integrate this experience into some automated tools that can help us along that side.
Okay, thank you.
Okay, thank you. Let's thank the speaker one more time. Thank you.